Assalamu alaikum, dear all, scientists, researchers, colleagues, students. My name is Dr. Ala Attar, and I am a mechanical engineering student, assistant professor in mechanical engineering, also a student. I am the Vice Dean of College of Engineering at Rabigh. Today, the Faculty of Engineering at Rabigh, collaborating with the Center of Excellence in Intelligent Engineering System, are honored and pleased to host Professor Jefsnyder to deliver his talk under the title of Design and Engineering of Thermoelectric Devices. Just to give you a brief biography about Dr. Snyder. Dr. Snyder obtained his Bachelor of Science in Physics, Chemistry, and Mathematics at Cornell University back in 1991, focusing on solid-state chemistry, which continued during 2-year stay at Max Planck Institute at Germany. He received his PhD in applied physics from Stanford University back in 1997, where he studied magnetic and magnetoelectric transport properties of metallic perovskites as Hertz Fellow. He was a senior member of technical staff in Thermoelectrics group at NASA Jet Propulsion Laboratory for 9 years, and the faculty associate in material science at the California Institute of Technology, Caltech, where he focused on he was focused on thermoelectric materials and devices. Dr. Snyder also now works as a professor he works as a professor at the Department of Material Science and Engineering at Northwestern University in Chicago. His interests include the discovery of new zental-phase thermoelectric materials and nanostructure thermoelectric composite using bulk processing and band structure engineering and thermoelectric performance optimization. Or thermoelectric performance, is it optimization? Yes. Dr. Snyder has published over 400 articles, books, chapters, and patents. He served as a treasurer of International Thermoelectric Society and vice president of International Thermoelectric Academy. According to Thomson Reuters in 2016, Dr. Snyder is one of the world's most prominent and highly cited scientists, particularly in the rapidly growing field on thermoelectric. Back in 2008, his review article in Nature Materials is used internationally to instruct many students and introduce the essentials of thermoelectricity to a multidisciplinary audience. It is the most cited article in thermoelectrics in 2013. With no further ado, I would like to introduce Dr. Snyder.
All right. Well, thank you very much for the very kind introduction and invitation to be here. This is my first trip to Saudi Arabia, and after living for 10 years in California, I'm happy to be back to a land that has so much sun and light, although I need to bring my hat. And now we're in, so when I was in California, one of the things that I studied I started off as a postdoc at the Jet Propulsion Laboratory in Pasadena, California, where we have developed thermoelectrics for space applications. And my goal in establishing the laboratory at Caltech and now moving to Chicago at Northwestern is to utilize these semiconductor technologies designed for space in terrestrial applications, such as for use in automobiles, in industrial waste heat recovery, or even solar power. If you're interested in learning about thermoelectrics more, I recommend our website at matsci.northwestern.edu. So a thermoelectric device is a solid-state device, meaning that it contains no moving parts, no fluids, and the fluid that we use is essentially an electron gas. So what we do is we have semiconductors that contain either excess holes in a p-type semiconductor or excess electrons in our n-type semiconductor. And we place these between a substrate that absorbs heat on one side and another substrate that rejects heat on the other side. Our thermoelectric device is equivalent to a heat engine that heat drives electricity. And the way I like to think about that is that heat pushes the carriers from the hot side to the cold side. So as the heat flows from hot to cold, it drags with it the holes and electrons. And by doing that, it sets up a electrostatic voltage that we measure as a voltage proportional to a temperature difference. And this proportionality constant we sometimes call the thermopower. Sometimes we'll technically call it the Seebeck coefficient because it's due to the Seebeck effect. Sometimes we use alpha, sometimes S in our equations for the Seebeck coefficient. Now, in a heat engine, what's more important than just the voltage is the efficiency. And so if you know about thermoelectrics, you've heard of the ZT parameter, where ZT is the Seebeck coefficient squared times temperature divided by the electrical resistance and thermal conductivity. And in the next slide, we'll get to a quick derivation of where this comes from. But for now, we can keep in mind that this ZT parameter is typically less than 1 for typical thermoelectric materials today. Although in the research environment now, we understand the physics and chemistry well enough, as described in the review article, that allows us now to get ZTs greater than 1 and up to around ZT of 2. So in a thermoelectric, we can think of our device as having an N-type. Device is made up of couples of N-type and P-type thermoelectric materials that are electrically connected at the hot side. And then through the cold side, we run the electricity through a load. And we talked about how the Seebeck effect tells us the voltage we get from the thermoelectric as proportional to the temperature difference. But we know that for a heat engine, we're interested in more than just voltage. We're interested in how much power. And power is voltage times current. So that means we need to have a large electrical current going through the system. And if our thermoelectric materials are too resistive, that will limit the amount of current. So we want our material to have a relatively large electrical conductivity to allow this current. So mathematically, we know that current times voltage is V squared over R, where R is the resistance of the circuit. And in this case, we're limited by the resistance of our thermoelectric material. So that means that our power from our device is proportional to the Seebeck coefficient squared from the V squared, but also now the electrical conductivity, where electrical conductivity is 1 over the electrical resistivity. And then also for power, we're going to have terms that depend on the outside parameters, such as the temperature difference across our device and the geometry of the device, the cross-sectional area and length of the device as well. But in terms of materials parameters, what we found is that the power depends on what we sometimes call the power factor, which is the Seebeck coefficient squared and electrical conductivity, as being the material parameters which help determine the power coming out of this system. Now, however, though, as we discussed this morning, that it's not, to get power requires more than just considering the electrical power. We need to think about the system, because these parameters determine power as well. And it turns out that for optimization, we actually want an efficient system. We want our heat engine to work as efficiently as possible, because in a system design, the true power comes from the efficiency times the heat flow through the system. So in thermoelectrics then, the real figure of merit is going to determine the efficiency rather than the power. And the most important parameter that gets added to this system, this problem, is the thermal conductivity, because it comes in through how much heat is removed in the system. So efficiency is power in divided by power, power out divided by power in, which is our electrical power, which we had from before. But from the heat removed part, the most important parameter we bring in is the thermal conduction. So where we characterize the thermal conduction through the thermal conductivity. I like to think of this as, if our material has a very high thermal conductivity, it acts as a thermal short where heat is quickly conducted from hot to cold. If we conduct heat from hot to cold without producing electricity, that will reduce our overall efficiency. Well, from this equation we can already see that the efficiency will have terms that include delta T and temperature, but also for the materials parameter, it will have this Seebeck coefficient squared times electrical conductivity over thermal conductivity by adding in the heat removed term. And so our figure of merit will be determined, our materials figure of merit will be determined by these three factors. And then when we do calculate the complete result, we will see that this ZT parameter, figure of merit, goes into a function which tells us our reduced efficiency, how much efficiency we get relative to our Carnot efficiency. And this allows us to then compare a thermoelectric heat engine to any other type of heat engine by comparing our relative efficiency relative to Carnot with other systems such as Brayton systems or Rankine systems. We will do the same thing for cooling as well. All right, so to give you an idea, now that we can do this comparison as to how thermoelectrics compare to other systems in terms of efficiency, well, right now we typically have ZT parameters on the order of about 0.7, so less than 1, which means our efficiencies are relatively low compared to the large electricity producing systems such as the Rankine systems used for coal or Stirling systems. And as we move to smaller size systems such as organic Rankine, even those systems tend to have higher system efficiencies than what we get with thermoelectrics. Now, with the technology that we're developing today, ZT of 2 is plausible eventually from this review article in 2009. But now since 2009, we've hit ZT of 2 in a number of materials. So I'm going to say ZT of 2 is an eventual case. And for these systems, we're becoming close to efficiency of some of these other systems, although it may be ambitious to assume that we will ever beat those other systems. And now, in terms of efficiency, but where we have the advantage in thermoelectrics are for the smaller systems. So if you are thinking of using thermoelectrics and want to think big, we need to think big, but in small devices, as opposed to large centralized systems.
Excuse me, sir.
Yes?
Radiation and convection, they don't affect the efficiency?
In our system, our fluid is an electron gas through the system. And so the equivalent of radiation and convection is already taken into account in our electron fluid. But if there is a true gas around the system, that would reduce efficiency. If we have a heat exchanger where we have a fluid-based heat exchanger to bring the heat into the system, those would also reduce efficiencies. So in order to design a real system, we have to couple with regular heat exchange concepts that might include fluid-based systems where radiation and convection are important. Okay, so thermoelectrics can also be used for cooling if run in reverse, just the way that a dynamic heat engine can be run into reverse to make a cooling system. And so in a thermoelectric, what we do is we take the same circuit, and instead of using it to power a load, we drive a current we drive a current that moves the heat from the top side to the bottom side. And then when we drive that current, it will then flow more heat than would naturally flow, or in other words, it makes the heat absorbing side cold and the heat rejection side hot. So in this way, we can pump heat. We can also lower the temperature and produce active cooling of a material. Now, because the system is essentially the same, we will use the same materials properties to determine the power and efficiency. So for example, the amount of heat that is moved from hot to cold depends on what is known as the Peltier effect, which is the rate of heat flow is proportional to the current, the electrical current moving through the system. And it turns out from thermodynamics, this proportionality constant is simply the Seebeck coefficient times temperature. And so then we will have a relationship between the heat flow in this Peltier cooler is very similar to what we had for the power factor and the temperature difference as well. And so again, when we're worried about losses now from the flow of heat back from hot to cold, we will need to include losses again, which will include this thermal conductive losses. And so we will derive again the exact same figure of merit for our thermoelectric device, Seebeck coefficient squared, electrical conductivity divided by thermal conductivity times temperature as our figure of merit, which determines again the irreversibility ratio, the ratio with respect to Carnot efficiency for Peltier cooling. Okay, so our thermoelectric then works like a heat engine, but the difference is that it has entirely solid state materials made from hard semiconductors. And so because the efficiency is not yet and may never be better than very large Rankine systems, for example, where we see these thermoelectrics are in small distributed devices that require these advantages, such as no moving parts, which leads to no maintenance, long life, and scalability to very small sizes. So we've been using these very successfully in power generation to convert heat to electricity in our spacecrafts. And the spacecrafts at NASA that use the thermoelectrics, such as these 3 radioisotope thermoelectric generators. And what they do is they bring a plutonium radioisotope heat source, which through the natural decay of the plutonium isotope produces heat with a lifetime of half-life of 90 years. And through that 90 years, the heat is converted to electricity to power this Cassini spacecraft, which was at Saturn for about 20 years, powering the communications and the sensors for this spacecraft. Voyager spacecraft has been successful using thermoelectrics now for over 40 years. It's the only man-made object ever to leave the solar system and has been communicating with us as to what exists outside our solar system. So they've been extremely successful and necessary for our space systems deep space systems. We are also now using them on our rovers for Mars. The latest Mars Curiosity rover has a thermoelectric generator to recharge the batteries. So this rover can operate at night, operate in the shadow of a crater, operate under the dust storms or winter conditions on Mars. This technology then can also be used for remote power sources on Earth, and so we'll see some examples of that as well. And the cooling side, we have actually a very large market for Peltier coolers for optoelectronics because the optoelectronics need to be kept at a very constant temperature, and the thermoelectrics, being solid state, can control temperature within 0.1 degrees or less. But we're now also seeing thermoelectrics being used in commercial cooling systems, such as small refrigerators, because the dynamic vapor cycle cooling systems aren't very efficient at these small scales, and so now the thermoelectrics, if a full redesign is done of the thermal system, then the efficiency of a thermoelectric refrigerator can be as good, perhaps even better, than traditional technologies. And what we'd like to do is, using the idea of cooling only where you need it and when you need it, as opposed to cooling everything from one centralized cooling source, we are hoping that that will help improve efficiency of even automotive cooling. So we'll talk about that in a minute as well. The other applications for thermoelectrics are for energy harvesting of remote power, or even a wristwatch, for example. Okay, so in the oil and gas industry, thermoelectrics are indeed used, although not terribly often. Today, mostly they're used for remote power systems, such as cathodic protection of pipelines for corrosion. But there's been quite a bit of interest in energy recovery, especially because during the oil and gas recovery, there's often flares that need to be burned off for the methane. And there, at least at one point in the US, there was regulation that these needed to be recovered in some sort of energy recovery system. So this is a design done by a startup company in the United States, where these flares are, the energy from those flares is converted using thermoelectrics into usable energy for energy recovery. Also, for smaller scale systems such as thermoelectric, so energy harvesting, where you can think of harvesting body heat from a watch, although the competition there is realizing that these systems are really competing with a battery, and so you really only want to use them in locations where you can't afford to replace a battery on the length scale of a year or two. So one possibility is very remote locations where you need self-powered communicating sensors, and this is where the oil and gas pipeline are essentially using those thermoelectric systems for cathodic protection as well as remote sensors for their pipelines. Other examples are, so we talk about remote sensors, wearable electronics, cook stoves. So for improved combustion efficiency, a cook stove could utilize extra air circulation, and the fan in there requires some electricity. Of course, there's plenty of heat in a cook stove, so we can use that to power that fan, and also provides a little off-grid power as well. Now, these small thermoelectric systems, in order to achieve a high voltage, are best made using small thermoelectrics. So there has been quite a bit of interest in using microelectronics technology to produce thermoelectrics at much smaller sizes. And so in principle, there are many different technologies. This is the thick photoresist technology that I worked on a number of years ago. But you can imagine many different ways to make a small thermoelectric device that will then give you higher voltage for thermal sensors or even a little extra power. For the climate-controlled seat technology, this is an idea that could have been around a long time ago, really is a fan and just a Peltier cooler, but has taken off quite a bit in the past, let's say 10 to 15 years for seat cooling. And this has the potential for improved energy efficiency as well, because we typically spend about 1 kilowatt of power running the air conditioning system in a vehicle, whereas a seat cooler would only use, say, 100 watts. And if we can utilize cooling only where it is needed, so for example, if there's a passenger occupied and there's detection of discomfort in the passenger, or when it is needed, such as the passenger arrived so we could rapidly cool them. Using these solid-state thermoelectrics, we could, in principle, reduce the energy consumption, not because of inherent efficiency of the compressor system or the cooling system. The coefficient of performance of the thermoelectric is not as good as the compressor, but the engineering system leads to an engineering advantage that could give you a significant systems improvement. So even though we hear quite a bit about ZT and improvements in ZT, I often think that the way to really utilize this thermoelectric technology is to think outside the coefficient of performance box and engineer a system to be smarter. Okay, so in electric vehicles, for example, we're going to be using the precious battery-powered electricity, and so we won't have quite as much power to be wasted on climate control. So for example, if we can only cool the seat and a little extra air perhaps at the face of the passenger that's in the vehicle, we could essentially save some power in that system design. Okay, so now for the rest of the talk, I'm going to go over some of the conceptual designs for a thermoelectric. Because, like I said, what I think a real advance in the technology would be not just the material that you see the papers about, but designing the hot side heat exchanger, the cold side heat exchanger, and then integrating that with a full system. So we'll talk about some general design concepts that I like to think about for how to integrate these thermoelectrics. And so we'll start with some of the simple energy laws that, for example, we know from the first law, we need to have conservation of energy. The amount of heat going into the system equals the amount of heat coming out of the system. And then we need to remember that the second law of thermodynamics says not only does the heat coming in equal the work out plus the hot side out, but that the work out is limited by the Carnot efficiency. And so what we remember is that for any thermal to electric generator that we have, regardless of the type, we have to consider the heat flows to understand how much power we get. And we have to know that we have to have that hot side heat exchanger to bring the heat in, and even perhaps more importantly, we need that cold side heat exchanger to bring this cold side heat out if we are to get any power through that system at all. in terms of a very simple electric circuit where we have our thermoelectric providing its Seebeck voltage. So the open circuit voltage is essentially the Seebeck coefficient times its delta T. And we can think of that as a battery in a simple circuit where our circuit not only drives electricity through our load, but our thermoelectric material also has its own internal resistance from those semiconductors that we have to consider. And so when we are looking at our voltage versus current of a thermoelectric device, it typically has a very simple load line in red from that open circuit voltage down to our closed circuit current, short-circuited current, which is a very linear load line. And what that means is that our power is then the current times the voltage is essentially a parabola that maximizes at a current about half the short circuit current and a voltage about half the open circuit voltage, making it a very simple system. Well, when we do that, what we're saying is that the internal resistance of the thermoelectric at maximum power is approximately load matched to our electrical resistance. And so and this is a standard electrical circuit that we know that in order to get maximum power out of the system, we need to have what we call electrical impedance match of that circuit. And what we're going to see is that we're going to have the same type of issue happen thermally. So if we think about our thermoelectric then being in a circuit with a thermal circuit with our heat exchanger and on the hot side and our heat exchanger on the cold side, we can draw a similar thermal circuit where for our thermal supply we have a temperature difference, and that temperature difference then feeds heat current through the hot side heat exchanger, through the thermoelectric, and then through the cold side heat exchanger, where the power producing temperature difference is the delta T across the thermoelectric device itself. But in order to get the heat current to flow through this thermoelectric, we have to have some temperature loss across both of our heat exchangers to make the heat flow. And so in our thermal circuit, we also have a system where we have essentially linear resistors hooked in series with a constant power supply. And so in order to get the maximum heat flow through our thermoelectric, heat power through our thermoelectric, we will need to thermally load match the system as well. And so what we'll find out is that the thermal impedance of the thermoelectric should match the thermal impedance of the heat exchangers. And so what we'll do is, we'll do this to first order. We'll make a thermal circuit model where we find an effective thermal heat exchange impedance, which is approximately the sum of our hot side and our cold side together, and draw a simple circuit again where we have the lumped sum thermal impedance and the thermoelectric thermal impedance in series. And once we do that, we come up with the same condition that we had for electrical, which is that for maximum power, heat power through our system, we should have thermal impedance match as well. Now, our power is due to our electrical power output of our system is due to the efficiency of that system times the heat flow through the system. And so what that means is that we can separate these two effects. We can maximize the heat flow power, which is due to thermal impedance matching. But then to maximize electrical power, it also means maximizing this efficiency. And we know that efficiency is maximized with our ZT equation. And so the conclusion then is that our ZT parameter, which determines efficiency, is also going to determine our power. So we are left with a relationship between our maximum power is our ZT parameter from the efficiency, and then through the thermal impedance matching, it says that our thermoelectric should be sized to be equal to our heat exchanger thermal impedance. Tells us that we will get the maximum power when we have our best designed heat exchanger. And so what this means is that, yes, we spend quite a bit of time optimizing ZT, but we would get just as much improvement, perhaps even more, by optimizing heat exchangers. And making these heat exchangers more efficient and less costly is going to directly impact our power. Okay, so our device efficiency then comes from ZT, and our power comes from ZT. And what we have to remember, though, is that when we are thinking about a device, we're using the device ZT, which we denote with a capital ZT, whereas our material parameter that we use often in many papers is the material ZT, which we denote with lowercase ZT. Now, approximately the device ZT is an average of our ZT as a function of temperature, but even that approximation is also just an approximation. But we need to keep that in mind when you're reading a thermoelectric paper and they say we have a peak ZT value of 2.6 or whatever. It doesn't mean that the average ZT or the effective device ZT will be that high. Typically, it's just an average. Okay, so there's also a bit of discussion about cost. Is ZT important, or is there a different metric for designing the cost of a thermoelectric system? And the best analysis, the most correct analysis that I think comes out of this is given by Chris Dames, where he has determined that the cost per watt, which is the metric for an effective system, really comes down to the cost per unit area of your heat exchanger. This is what's really going to dominate the cost of the system, not so much the materials cost. So even at $200 a kilogram for bismuth telluride, the dominant cost of the system is that heat exchanger. And then in order to get the power out of that system, the average device ZT is what matters. And so the cost per watt is essentially the heat exchanger cost and the ZT. So again, the ZT is the cost metric. So if you're going to design a system for cost, I still say work with your highest ZT materials. But work on those heat exchangers. Okay, so for our power then, we had a simple estimate of how much electrical power, which is going to depend on our heat exchanger parameter and our efficiency. And that allows us to get a pretty good estimate for how much power we will get out of a thermoelectric system. So for example, if given the supply temperature between the very hot side and the cold side of the system, we can assume that we're only going to get about half of that delta T across the thermoelectric in the most optimized system. And then, in order to get the most power, we are going to really have to be engineering that heat exchanger. And so those systems are typically limited by how we're going to do it. If it's a forced air heat exchanger, we get a relatively low value for heat exchange coefficient. And if we move to forced water, we might get a significantly higher. But we have to make that system-wide decision. One can one can estimate the thermoelectric performance simply by using the relative efficiency relative to Carnot for a thermoelectric system is usually between 10 and 20%. Okay, so as a simple example, let's consider a typical wristwatch. How much power could we get out of a wristwatch? Well, we know how much body heat we produce. We produce about 100 watts of heat over the size of about 2 square meters. And so that means we get about 20 milliwatts per square centimeter. For a skin temperature of 33 degrees Celsius, room temperature 21, that's our temperature, 12 Kelvin temperature difference between the hot side and the cold side ambient, which means that under thermal impedance match, we would only get at most 6 Kelvin across our thermoelectric, which means the Carnot efficiency is already 2%. If we have our reduced efficiency of 20, that means the total efficiency we should really ever expect is no more than 0.4%, or about 80 microwatts per square centimeter. So for the Seiko wristwatch that we helped design years ago, they made a module that had about 22 microwatts of output from 10 modules. They had about 1.5 Kelvin across the thermoelectric, which is pretty good, of similar order of what we expected was maximum power out of the system of 80 microwatts. So this method of approximating the power seems to be reasonable with experiments, and gives us a good estimate to how much power we could expect for a wearable device. Okay, so there are some other issues that are associated with these high temperature modules. If we typically will make a prototype module, NNP materials, and a hot side interconnect, and then all of that on top of a cold side substrate. And when we make these devices, there's typically a fabrication step that leads to very large stresses due to thermal expansion mismatches. And those stresses tend to be concentrated at the hot side of the module. And that leads to breaking at the interface. And so here's a SEM picture of hot electrical connect with the thermoelectric, and then a crack running through the material, which of course is going to lead to failure. And so there is opportunity for materials research in other ways. So for example, looking at diffusion barriers to improve that contact, make sure it doesn't break, and also doesn't allow interdiffusion. So for example, if we tried to improve that connection with a nickel interconnect, after a number of hours we'd start to see voids being produced in secondary phases, whereas if we develop other diffusion barriers such as this zirconium-based metallic glass, we can have, after 360 hours, fairly good looking interfaces. Okay, so let me summarize and say that thermoelectrics are very promising for energy harvesting and solid state cooling, and that there are a number of design issues that we should consider for developing these smaller distributed technologies for large-scale applications. We talked about the thermodynamic issues. The heat exchanger issues are quite important due to the impedance matching conditions, both electrical and thermal, that determine the electrical output of the device. And also some mechanical issues which are also rarely studied in the field, but are going to be very important for real systems. And with that, I'd like to thank you for your attention and acknowledge my great team at Northwestern.
Thank you, Dr. Snyder. I think we give the priority for the students first to ask questions, and then after that, our colleagues, if they want to ask questions. And I would say you can lead the Q&A session.
Okay, sure. So any questions from students first?
Come on, students.
Someone's got to break the ice.
Yes, come on. I wish I was.
Maybe.
Anybody else want to help them break the ice?
I've got a question about the applications, because it seems thermoelectric might work very well with the solar PV systems. I mean, to absorb the heat
Yes.
usually associated with solar PVs
Yes.
and generate extra.
تعالي صوتك دكتور عشان نسمع الناس. Sorry.
Yeah, so the question I believe is there a opportunity for thermoelectrics to assist photovoltaics because of all the heat that's produced in collecting the solar power, I believe.
They are from the same family, I mean, using the
Yes, so this has been an idea that comes up. There's a number of different ways to solve this, and the real problem is that the photovoltaic collector. So if you use a standard silicon photovoltaic device, the efficiency of the photovoltaic depends on temperature. So, or at least, so the silicon ones in particular have lower efficiency as they get hotter. But the thermoelectric needs a hot heat source to be efficient. And so there's a bit of a trade-off as to what temperature would you want this junction to be. If you just put the photovoltaic here as your heat absorber, then the thermoelectric would work best if it got hot, but the photovoltaic works best if you cool it. And it turns out that with the temperature coefficient of efficiency for a silicon solar cell, it's not really worth heating it up at all to use the thermoelectric. In fact, it would be better to cool the system to get more efficiency from the photovoltaic. Now, if there are other systems that, photovoltaic systems, that would be different. So large band gap systems that have a different temperature coefficient of efficiency, it would work. If we can develop technology to separate the visible spectrum from the infrared, then it would help both sides because you wouldn't heat up the photovoltaic so much. So that's probably the most promising way to do it in thermoelectrics. Yes?
Thank you very much for this excellent presentation about such excellent technology. But I'm not in a field, but I would like to ask about one aspect, and how much this technology could be affected by the outsider environment. You know, here in the winter,
Yes.
summer is very hot, so
Yes.
what do you think about it?
Well, so this technology handles heat best, but it doesn't handle oxidation. It doesn't handle water very well. So these thermoelectric materials typically need to be protected when they're at high temperature in a power generating device. They typically need to be protected from water and air. The cooling systems, it's less important because the reactivity depends on temperature. Yes?
Maybe my question related to within the question said, what is the effect of convection? And the source of heat maybe is a body source, no body heat source, it's radiated. So what is the effect of this? Even the crack, when you talk about the failure in cracks between the materials, I think this fluid. We have already did research using level sequencer to follow these cracks between two faces. So what is the effect of fluid dynamics and thermodynamics?
Well, I mean, I think this is a very good question in that the traditional thermoelectric field does not spend enough time thinking about these issues. That 90%, 95% of the thermoelectric folks you will run into at the ICT, for example, are just looking at this material. And they're ignoring the effects of the heat exchanger in the system. And yes, you know, the convection that goes on in these cold side heat exchangers makes all the difference in the world as to whether you get the equivalent of the you know, forced water or forced air heat exchange coefficient. So if you've got technologies that can get us to this value, but without having a high pressure water system, but having, you know, natural convection air, but just playing around with nanostructures and natural convection, then that would make a big difference in the cost and utility of these systems in ways that most of the community isn't even looking at. And then I have to admit that the thermoelectric community does not spend enough time looking at these interfacial issues where there's a whole industry out there that looks at bonding and thermal expansion coefficients between different metals. Now, this is a different problem maybe than what you're used to in that our thermoelectric material is a brittle material that is, it's not as brittle as the ceramic materials maybe you're used to, but is more like the ceramic than this metal. There's an interface. And it depends on the electrical conductivity of the material. Yes?
Regarding this question, you see now in the equation you have delta T, which is current equal thermal resistance, right? Yeah. You can add thermal resistance here. You have theta Hx and here in this circuit.
Yes.
Yeah, here. In theta Hx and theta Te.
Yes.
You can add another convection resistance, which is proportional to the heat transfer coefficient.
Yeah, so that's all buried in there, yes.
Another theta, and this include the convection.
Yes.
Yeah. But yeah, this is one thing. The other thing, I need just clarify some symbol for conduction. You have the conduction equation, the first slide or something. Yeah, there is a first slide.
The very, very first slide.
There's something yeah, there's something. First, maybe second slide. Yeah,
Here, this.
Before that. Yes, here, yeah, this one. Now, this delta T or gradient T. K is gradient or delta. Because using the delta T is the temperature difference. But gradient is different. Conduction is defined by gradient, not delta. This is one thing. And the other thing, you put this as a Q, and the other thing you put Q dot.
Yeah.
We need to be this inconsistency.
Yeah. The notation of our community with Q and Q dot is not optimal.
You use the Q dot as a power, right?
Yeah.
With efficiency, but here it's Q. It's supposed to be the same.
Right. No, you're right.
And the delta is supposed to be gradient, not delta, because use delta T as this Carnot efficiency. It's the temperature difference over TH.
Yeah.
Yeah, then the conductivity is supposed to be gradient.
Well, okay, so so the problem is that there's the traditional way to do this equation is to look not locally but to look globally at the full system.
Yeah, but the definition of conduction itself, it is related to the gradient. It's not the difference.
No, I totally agree. I agree that that traditionally we do it wrong, okay? And the problem is that to the thermoelectric community, you know, if I talk about heat removed, they expect me to write these three terms, okay? The conduction term, the Peltier term, and this heat source term.
To clarify the notation between Q, kilowatt, and the...
Yeah. Well, no, so this is a good point, because I spent about 5 years of my career converting back to the gradient term. And when you put the gradient in here, you get rid of this, which simplifies the problem at all. But then most of the people in my community won't recognize it. So, but you're right that the well-defined efficiency is only at that hot end, and that hot end you would use the gradient here, and this is the hot end term, but then that would go away.
Yeah, there's one last thing about it.
Yep.
Any research for comparison between PV and this one regarding as you saw cost per unit watt, if there is any comparison?
Well, yes. The problem is that the cost of PV has now dropped so fast that we don't compete at all anymore.
Because you can use for solar cell here, especially in Saudi Arabia, they have a lot of sun.
Yes.
How to adapt it
Yes.
to the solar energy?
Yeah. So the only way, so if you do concentrated solar, and then you're going to save the heat, you know, for nighttime production, then we can start to compare the thermoelectric again to other heat engines. But even then, you know, if you have an efficient Rankine or Stirling or other true thermal to electric system, you're going to outperform the thermoelectric. So we've had a couple solar programs, but they really don't compete financially. Yes.
I would like to thank you very much indeed for your extremely interesting presentation. For somebody like me who doesn't know much about the subject, you've done a great job now. I really understood most of what you said. I would like to welcome you at KAU. Most welcome to be with us. We are honored and privileged to have you at King Abdulaziz University. So you are most welcome. You are also most welcome at this lovely country of Saudi Arabia. So most welcome.
Thank you very much.
And I also would like to welcome my friends and colleagues and the students from Rabigh. Most welcome at King Abdulaziz University. Probably it's your university. Probably you graduated from here. I don't know. Most welcome. I don't have really questions. Just I like to welcome you.
Thank you. Yes.
There is a report that the figure of merit for nanostructures has higher value.
Yes.
For some nanostructures.
Yes.
Is there any devices built on the basis of some nanostructures? If it is not, what is the scale or what is the sharing?
So none of the, I guess the short answer is none of the nanostructure design devices have yet to have reliably improved efficiency such that the industry is using them. I would say that there is a good possibility we can improve average ZT using some of the nanostructured concepts, although some of the nanostructured concepts you may have read about, we've already shown they don't really work.
Because you know, nanostructure, they have the thermal conductivity is low.
Yes.
The green side.
That one works, yes.
But what is the mean challenge here in this way?
What is the mean?
Challenge of using nanostructure.
Challenge.
Because now 20 years people working on nanostructure or more, nothing yet come to the 5 meter. Must be, you know, some reason behind it.
Well, I would say some of those effects probably are already in commercial materials. So polycrystalline bismuth telluride has some grain boundary effects. So most commercial materials are bismuth telluride, and because it's an anisotropic material, it's very complicated. So I believe we can improve the average ZT of bismuth telluride by 10, 20, 30% if we include nanostructure, but all of the other concepts that we have as well. But we may only improve it by 30%, where if we do improve system efficiency by a factor of 5 or 10.
100%.
Well, right. So, right.
Because in your engineering, we're looking for 2%, 1%.
Right, so the bismuth telluride companies, if we could reliably produce 10% better material, they would buy it and it would be used.
I think we need to end up that session today. If anyone, I want to ask Dr. Snyder questions, maybe after the session. Thank you all for coming. And thank you, Dr. Snyder.
Thank you.
Thank you very much.
Thank you.
Yeah, he'll be hanging around for a few minutes if you want to ask him any questions privately. Say.